This is a hangout that we've organized, or rather we should call it a Zoom meeting now, that we've organized for our learners in the Coursera course on 3D printing, which is offered by the Illinois Maker Lab in partnership with Ultimaker and Autodesk. And this is, we are about week 2 into the second course in the specialization, and that is the 3D printing applications course. And today's talk with Dr. Charles Mire is looking at sort of the possibilities of 3D printing with soft materials. And one of the, I actually, got to know of Dr. Charles Mire when we were looking at one of the projects that actually I mentioned in the course as well, is the 3D printing with food in done by one of the students in our university. And that's how I got to know of him. And once I contacted him, I realized that what their vision for their particular hardware solution that they found was much bigger than just food printing. So we are going to learn about that today. So Charles, let's just start by introducing yourself and tell us about your history and how you got interested in this space. And
Very
then
good.
Perhaps your firm is not too old, so I could call it a startup.
Yes, exactly. Well, and yeah, it still is very much a startup. So
over to you.
Okay, so some background. How did I get into 3D printing? Some of it was a little bit accidental. I had a career in IT, and I intended to transition to a career as a scientist. And so I started, my advanced science degrees and so on, and got a scholarship to do my PhD in Australia. And so that started in 2007. And my project was to print conducting polymers and biopolymer materials. I started out with inkjet printing, and found that to be immensely frustrating when you're trying to formulate custom materials. And so I started looking at a larger scale, on the micro scale of printing. And of course, that was extrusion. And that's where 3D printing fits in. Now, in 2007, you could not buy a desktop 3D printer. You could not buy a kit. There was no open source models or anything like that. It was very early. I think the Prusa was just becoming coming out, or the RepRap, I think. And so it was too early, and I didn't want to waste my PhD time trying to build a printer because I had to get a PhD in chemistry. And so I went ahead and I bought a desktop CNC milling machine, and then I connected a syringe to that and built an interface for that. And that became a system that I could print soft materials with. So in building that, I learned a lot about the fundamentals of a 3D printer system, and then finished my PhD and officially graduated in 2011. And by that time, I think Ultimaker was founded in 2011. So, and the RepRap movement was taking off more. So anyway, that's essentially the background that led me to this point now. And I watched the 3D printing market rise, and I thought, okay, surely somebody's going to invent for soft materials. Yeah. And because, from my studies, I saw that there were a lot of useful materials for soft material, for printing that were in soft form. And to my surprise, nobody came up with this product. There were some companies who tried. There was the Fab at Home group from MIT, for example. And there were, there's Rich Wrap, which is an open source type of paste extruder. And I think PrinterBot has an open source paste extruder now as well that works on their printers. So, so it's clear that other people are trying to solve the problem. But what we did that was very different was we put the mechanics separately. Then you don't have to mount the mechanics on top of your printer. And so this makes it to where we can put a lot more power into our system. And so the way our system works, it's a tower that stands next to your printer. You put the cartridge in and you connect a tube over to your printer. So the physical mounting is just a tube, which is trivial. Okay. And so this way, we tried to ensure wide compatibility. And so the Discovery is driven by a NEMA 17 stepper motor, and which is compatible with most 3D printers. The only printers that seem to have problems that are semi-open source are the MakerBot platforms, things like the FlashForge or the Wanhals and all that. MakerBot made some design decisions that deviated from the standard that the rest of the 3D printing world is following, as well as proprietary printers. So if you have a 3D Systems Cube or something like that, there's not, unless you're a genius electrical engineer and you want to spend time on that, it's probably not going to happen. So, okay, so I see a question actually in the chat. Extruder account for shrinkage factor with different materials, and if you were to work on a project that is sensitive to the size of the product, is there any way to compensate for the shrinkage of the part? And so that's a very good question. So what this involves, it involves your concentration of your material with respect to your solvent. So if I have a material such as silicone, silicone does not really exhibit noticeable shrinkage when it dries. So typically when we print a product out of silicone, it's the same dimension as we intend it to be. So so silicone is just kind of a special material like that. However, if I have something that is a hydrogel material or something that is going to dry up significantly, then the printed structure will have to be tuned so to allow for that drying factor. Basically the printing aspect is just a tool, but it does not solve the materials problem. So so the Discovery extruder is intended to allow you to bring your own materials to 3D printing, but the material problem itself, when you're working with your own custom materials, is truly up to you. So that is a problem that has to be accounted for with respect to your design.
So Charles, just to sort of set the canvas, I know everybody thinks of, looks at this Discovery, and we look at printing with, food, and everybody gets sort of sidetracked from the conversation on what soft materials really can do. And I know you have explored applications far beyond just foods in terms of electronics and tissue engineering.
Yes.
And even edible electronics. So just give us a lay of the land as to what's possible with soft materials right now.
The possibility with soft materials, essentially, if you look at 3D printing before Structured came along, you had a handful of plastic materials, maybe 12 in the beginning, maybe about 40 to 50 plastic materials now. Lots of different kinds of PLA, ABS, you have PEEK, you have polycarbonate materials, you have carbon fiber type filaments now. And then you have semi-flexible materials like NinjaPlex and so on. But the important thing to remember about all these materials is they're fundamentally plastic-based. And they're fundamentally thermoplastics, meaning they require melting in order to deposit into your shape. What that means is then if you want to have something that is a gasket that is going to go on an engine of a car and you need some flexibility, okay, that's great. You got NinjaPlex, but as soon as you turn that car on, it gets hot, that NinjaPlex is now going to melt. Again, so you cannot use any of these thermoplastic materials for heat sensitive applications, since that's the mechanism that is used for the printing. So that's where the softer materials come in and open the possibilities up even further. So when you start talking about soft materials, it's a little bit easier. If you have some chemistry background, advanced chemistry, you can do some pretty cool stuff. If you just have some basic chemistry background, you can still do some very interesting material formulations all on your own, and then you control that recipe. So because of that now, it goes from, say, 40 or 50 materials for 3D printing to thousands of materials for 3D printing. And what that means is it allows you to take advantage of the benefits of 3D printing even better, because the benefit of 3D printing is not mass manufacturing because 3D printers are inherently slow. The benefit of 3D printing is customization, getting that very specific thing to solve your specific problem. And when you only have 50 materials to choose from with filament, for example, that just gives you a very limited choice in solving your problem. And many of those choices might be good. Obviously, if plastic is the right material, use plastic. It doesn't have to be soft materials, but there are applications where soft materials are very beneficial, and having thousands of possibilities there allows you to find exactly the right one. So to go into some actual applications, I mentioned gaskets. So if you have an older car, or if you are making a custom type of engine and you machine the engine block and whatever, but now you need some custom gaskets. So how do you make that? The traditional method would be to get a flat sheet of silicone rubber or some other heat resistant rubber, and you cut the holes in it, and you hope that you can do a good job cutting it and not leave any gaps and so on. But with the discovery, you can actually get proper gasket silicone that will have the heat resistance, the oil resistance, and then you could print them, and you could print multiple copies of them. So that's one benefit there. And then if you start looking at, say, medical prosthetics, for example, if somebody wants, everyone's body is so different and so, shape, size, everything. So if you need a medical prosthetic, the traditional method is making a mold. Very time consuming, and then you have to store the mold. So you're paying storage costs. And then if you lose it, it's time consuming again to make another one. Whereas the 3D printed design, the design can live up in the cloud, and you could be anywhere in the world and you lose your prosthetic and you need a new one, and you go to a local print shop that can print a silicone material. You call your doctor up on the other side of the world and you say, hey, can you send my print file to this guy so he can print me a new prosthetic or something, so you don't have that in any other situation. So and then if we talk in of opportunities, something like tissue engineering. Right now, there are problems with organ donation. So if somebody needs a new liver or say a new heart or any other organ in their body, you have to find the right kind of donor. You have to find a match. Even if you find a match, though, you are taking a lifetime of anti-rejection drugs because your body recognizes this organ from somebody else as a foreign object and will attack it. And so that becomes a dependency that, okay, sure, you're alive, but nevertheless, now this is a factor for the rest of your life, taking those anti-rejection drugs. Whereas with tissue engineering, the promise of tissue engineering is that you can print a neutral scaffold material and you can seed it with cells from the patient themselves. So if I need a new liver, they can take healthy liver cells from my body, put it on this scaffold, let it grow in the lab until it's the right size and ready to continue growing and becoming a part of my body. They plant it in me, and because it's my own cells, now I no longer have this anti-rejection drug issue to worry about. And then, and yes, so the answer here is tissue engineering the same as bioprinting? In many respects, yes. I would say tissue engineering is probably a little bit more advanced than bioprinting, and I'll get into, I think, what is the subtle difference there. So now, some of the challenges still with tissue engineering, we're going to see this in the real world, I think, probably in the next, say, 10 to 20 years. Because if I can print a scaffold and grow liver cells on it, that's great. And this is one of the slides in the presentation I sent you, Vishal. So that's one problem. But the second problem is you have to get blood flow to this organ. So you have to have a vascular network inside of your 3D printed structure. So that way you can attach it to the arteries and get blood flow into the system, because if the cells don't get blood, once they're in your body, they don't survive. So then now you have to incorporate that design into your 3D print. And then secondary is that the materials for the vascular network might be very different than the material for the structure of the organ. Okay, the vascular network might be a little bit of a muscular type of structure. And okay, so yes, so here's a fantastic slide that kind of highlights, where some of the current state of the research in the tissue engineering side of things. So, so this one up in the top left here, it shows these little lattice type of networks. This is a survey publication from the year 2000. And the reason I put that in this talk is to show you 16 years ago, there was already an established body of research talking about the possibility of printing these scalpels for bone and cartilage. And then over in the upper right, the Nature article there, this is by a professor at Harvard named Jennifer Lewis. And what she showed is that you could use temperature properties with soft materials to where you have the melting point of different materials that, or two materials that have different melting points, in other words. So where you have one material that when it reaches room temperature liquefies, and another material when it reaches room temperature solidifies. And so you print these two materials together, and when the secondary material reaches room temperature and liquefies, that becomes your vascular network, and you simply pour that material now as a liquid out of your 3D printed structure, and you're left with the form factor of a vascular network. And so on the bottom here, what I'm showing as well, when you think of tissue engineering, it's not just a magic, oh, I found a great tissue that cells grow on or something like that. There's a lot more to it. So the first picture A there shows that you have to test the mechanical strength of the printed material. If the material does not hold up to the mechanical strength that you expect it to be able to withstand once it is in the body, it is not going to work as that organ. So then you have to start again until you find the right mechanical strength. Okay, so now you found a material with the right mechanical strength. Now you go to step B. Step B is, can you make it into the shape that you want? So if you can make it into a custom shape, then okay, that's great. That will work. Now you go to the third step, which is, can you grow cells on it? So if you cannot grow cells on it, then you go all the way back to the beginning and start all over again. So this is why tissue engineering is 10 to 20 years off, because it's a very, very big problem. And there's and it's even more complex than just these three layers that I've shown here. If you think of the typical organ, it's got about 9 or 10, maybe 15 different cell types that are all working together to make this organ. You have cartilage, you have connected tissues, you have the vascular network, you have the actual cells themselves, doing the function for that organ. So it's a very, very complex problem. Now, if they solve it though, then you can imagine that even as you get older, and for example, you get cancer in your pancreas, for example, okay, well, then you can get some good cells that are left in your pancreas and have the laboratory at your hospital grow you a new pancreas. And so pancreatic cancer is a very difficult cancer today. And so you could potentially cure cancer sort of on the back side of this by being able to fully remove a cancerous organ and replace it with a new one. And so that extends the lifespan of people. So there's lots of promise in that, but nevertheless, it's a very, very busy area of research now. So.
Great. Well, thanks. I know that's a lot of information for people to digest, and we hear about bioprinting from Dr. Tolu Shokufar at UI Chicago. And in fact, Jennifer Lewis that you mentioned was at UIUC before she went to Harvard. So,
yes.
She's done a lot of work in printing with, not just on the vascular network, but on printing with electrically conductive inks. And they have the Voxel platform.
Yes.
That's pretty impressive.
Yes.
So perhaps let's talk about the edible part, and that's your sort of the next use case or the third use case for soft materials. Tell us about this.
Yep. And so, so the upper left-hand picture, this is my PhD supervisor, and he is still using the 3D printer system that I built at the university, which is right below him, that black CNC milling machine. Now, in the top two pictures, he is talking about thermally actuating hydrogels. And so this is another type of, it's commonly called 4D printing. So 4D is it's kind of a buzzword used by the media. In the academic world, it doesn't they don't talk about it necessarily the same way. So, but what this means is that you have materials with other properties that can change the shape after you printed them. So printing obviously is 3D. And then now in this case with these hydrogel materials, they have some, they're chemically tuned so that way when you change the temperature, they either expand or shrink. And there's a lot of materials that will behave in a similar fashion. So, but you can take advantage of that type of material then and 3D print it. And then you end up with a device that might not be possible at all with traditional manufacturing. So in this case, they're talking about the a smart valve that you need the valve to just simply respond to temperature whenever the temperature occurs. You don't want to put any electronics in there or anything like that, because that means extra logic. And, you know, if the software didn't think of all the scenarios, then you're limited in the functionality of the device. But if you make it a simple binary type of device where it either responds to hot or cold, whatever that range of temperature is, and then it just simply works, then that's a much better device in certain situations. So now the food printing side of it. So everybody, I'm sure, has seen the 3D printing Nutella that Structured has done, and other people have done some 3D printed food in terms of showing off the artistry of the 3D printed food. But there is also some interesting things that you can do with food chemistry in terms of electronics. So in this case, Vegemite is an Australian product. It's made from beer waste. Not everybody likes this food. It's very salty, and it's it's an acquired taste, definitely. Now, because of the salt content, though, it will convert to electricity. Yeah, exactly. So when you realize that foods have properties such as this, it means that we can do other things with the food that are just outside of the normal range of things. So, and we live in a very good time where we can play with our food like this. So the idea here is that, well, there's Vegemite printed on a piece of bread, and you have the wires connected, and it's lighting up the LED. So it shows that you can make a complete circuit with things like that. Obviously, this is just a proof of concept. However, if you think of hydrogel materials or other biological materials, you have sodium alginate, for example, which is a brown seaweed extract used as a thickener in foods. And you can do some chemistry with that. You could also do some chemistry with sodium alginate and calcium chloride, for example. And when you have all those options for food chemistry, you have cellulose that's often added as a thickener. You can then make something that might not be the most tasty food, but it may have some fantastic functionality, say, as an electronic type of device. And where this could be used in a practical sense would be, imagine medicine, for example. So right now, most people take a medicine in a hard pill format. So if you need to take a giant pill or whatever, and it's hard like a rock, it's very hard to swallow that. And so now, if you have something like a printed electronic type of device, then you could potentially incorporate drug release. You could have an edible battery inside there as well.
Yeah.
So then, you swallow this soft, squishy pill that's maybe, almost like a piece of Jell-O. And so it's much easier to swallow and get a larger dosage of a drug. And then you still have the time release benefit that you get out of the hard capsule. So that's a very simple idea, but there are similar ideas as well. If you want to go onto the Star Trek side of things, where you have these nano electronics that go in your body and do stuff to repair your body and then dissolve after 10 days or something. So
let's take some of the questions that are there in the Q&A. If you want to open that, and we can just start from the top.
All right.
So first is from Nagarajan, who's looking at what kind of extruder he should use on the Prusa or any other printer for sugar-based food substances.
You can use, well, the Discovery would work on the Prusa. The Rich Wrap would also work on the Prusa. The PrinterBot extruder would probably also work on the Prusa. So there are many paste extruders that will work if you're just looking for printing sugar-based substances like an icy. Now, keep in mind, each of these extruders work a little bit differently. So the way that you would mount the Rich Wrap extruder will be different than the way you would mount the Discovery or the PrinterBot extruder. And so when you decide on which extruder you'd like to use, then that's what you have to think about with the customization. So so the Rich Wrap is an open source design. You can download it and print it yourself and source the parts. So if you're very new to the idea of printing soft materials and you're not sure if you want to spend the money on a Discovery extruder yet, you know, the Rich Wrap is a great way to go to test out to see if this is something that's interesting for you.
So the next question was on printing electrical conductive materials. So does the Discovery handle those?
Yes. So if you were printing, so one example that we have shown with the Discovery is printing a material called Bare Conductive, B-A-R-E, conductive. I'll type that up in the chat.
I can type that in. You go ahead. Yeah.
Okay. So what that is it's a carbon-based paint. So it's low conductivity. It's not like a metal or anything like that, but you can still make, you know, basic electronics with something like that. We printed a fractal antenna onto overhead transparency. So you can make flexible electronics that way. Now, if you want to get into more advanced materials, so my PhD work involved conducting polymers. So I was printing a well-known conducting polymer is one called P.PSS. So that one is often used for solar cell applications and you know, other types of electronics. I did some printing with carbon nanotubes and graphene. And but if you wanted to look at something that's a bit more standard for electronics, silver nanoparticle paste, and specifically nanoparticle. There are companies like Dow Chemical that make a microparticle paste, but the particle size is large enough that if you printed the microparticle paste, you end up having to put your print into a reflow oven in order to sinter the metal and make the electronics actually work. Now, with nanoparticle paste, you can do something called flash sintering, and I'll get into that in a minute, but that is one of the electrical conducting materials that you can print that's very close to the real world. Now, the nanoparticle, both of these things being silver, they're not cheap. They're very expensive. You're paying the price for bulk silver. You can also buy gold nanoparticles, platinum nanoparticles, and every single one of those is priced just like the precious metal. Now, I was talking about flash sintering. So what that means is you can use a light bulb to sinter the metal. And it's a fantastic physics trick, essentially. And so what you're doing is you're taking advantage of something called the photoelectric effect, which is what Einstein won the Nobel Prize for. I'll type this. So you use a broad spectrum 200 watt mercury, and basically you flash it like a flash bulb of a camera, and it causes the nanoparticle silver to just fuse together. So you don't need an oven. And so you lower your electric costs for making electronics like that. And then that also allows you to print silver nanoparticle paste on something like a plastic overhead transparency, which cannot go in a reflow oven. And so then you got flexible electronics. You can print on fabric, you know, all those other kinds of things. So, all right, so now embedded electronics inside a silicone wrap. That is also possible. However, if you are going to make that, the way I would recommend doing that on a 3D printer is to put the silicone first, say a silicone membrane or something like that, very thin sheet of silicone, then let that cure first. Then you print your electronics onto that cured piece of silicone. Now, the reason why is because silicone, when it's not cured, is wet and sticky. And when you are 3D printing, that first layer of whatever material you're printing needs to stick. If you try to print another material onto wet, sticky silicone, the material and the tip is going to get dragged through the silicone, so you're not going to get a very good print. But if you have a solid surface, whether it is a solid rubber surface or a hard surface, then that material will stick, and the tip where the material is extruding from will continue to move properly and lay down a consistent pattern for you. So that's the way I would approach that, and that is a way to make the strain gauge type of soft sensor. Now, there is another way to do this that is a little bit more advanced, and this is also shown in one of the slides, where you can do submerged printing. Now, the Discovery extruder really works well for submerged printing, and now the other extruders could as well, but the weight is a little bit of a factor here in terms of, and also precisely controlling your printer by not having a lot of weight mounted on your nozzle head. And so the Discovery is the lightest weight that's mounted on your nozzle head. Now, so the way you would do this is you would use a longer needle, and so a blunt tip needle, not a sharp needle. And so the longer needles are, say, maybe 1 or 2 inches, about 4 centimeters, 2 to 4 centimeters in length. And what you would do here is you would have your silicone rubber or something like that that is still wet. Okay, and so you could have platinum cured silicone or something like that, to where you've got, say, 4 hours or whatever before it's going to cure, and it's like water. So then you can extrude a conducting polymer or a silver nanoparticle line inside that silicone. Okay, so you basically plunge that needle into the silicone, and then you print this line inside the silicone, and then you pull the needle out and then let that silicone cure, and now you got an electrical conduit inside that silicone. Okay, this gets a little bit tricky with the fluid mechanics side of it. So you have to make sure that your the flow resistance of your two materials are compatible. Okay, so if it's very watery, you don't want your material sticking around on your needle and not laying a nice line inside your silicone. Okay, so that takes a little bit of optimization, and it's different for different materials. Also, a good way to also play around with this is if you have a natural phase separation with materials. So for example, when I did some printing just like this, printing P.PSS inside chitosan, and these two materials had phase separation. So if I stir them together in a jar, it's going to look like egg drop soup. Okay, I'm going to have these black flakes or whatever, so it's not going to mix with this hydrogel material. And the reason why was because both of these had, if I remember correctly, they were both positively charged. Okay, so they were repelling each other based on their strong positive charges. Okay, so so that allowed me to print submerged electronics. And so, all right.
Great, thank you for that. I think we'll sort of try and close up the session. You know, I know Fam is asking for some discounts. I know your answer to that, so I can answer that for her. You know, I asked him for a discount for the lab ourselves, and he said they're still a startup, so they need all the funds they can get. So we won't be able to get you discounts from Charles for the
right. Yeah. So now the other side of this is that even though we don't offer a discount, we do share a lot of our knowledge. Okay, yeah. So you know, if you buy this and you have questions or whatever, we'll definitely try to help you out. So so that's kind of where the value add is there.
No, certainly. I think there are, you know, from your expertise on several of the open source alternatives, I think those who cannot reach that price point can certainly, you know, figure out ways to hack together a solution. So just to sort of closing thoughts on sort of what is the future that you're excited about in this space?
Sure. So future that I'm excited about is I want to see, well, first of all, I'm very impressed with the 3D printing community as a whole. It's grown. So even though it's very, you know, consumer centric and things like that, it's become a tool where each of us can solve a lot of problems that we have a personal connection to some way or another. And so I love that aspect about 3D printing. And now I'm very curious to see, as paste soft materials printing becomes more mainstream, what creative people do with that capability. So that's where I'm very, very excited. So both at the the university and the research level, as well as the the level on the ground where people are just solving unique problems on their own, I expect to see a lot of interesting developments over the coming years in that area.
So thank you for your time, Charles.
Thank you.
And thank you to all the viewers for joining in, and see you in class.